Welcome back, ladies and gentlemen. In this video, we're going to look at how we can solve some problems in projectile motion. So dive right into the problems since we already have the notes. So here's the file I have opened already and some questions. So the first question is saying the ball is projected from a position a distance 4 meters horizontally. As you can see in the diagram here, it's 4 meters horizontally and 1 meter vertically from the basket. As you can see from the basket vertically going up, it's 1 meter as shown here on the right side. Now this is with a speed of v meters per second at an angle of alpha to the horizontal. So this angle is alpha. Okay, the angle of projection is alpha. Now the ball falls into the basket. Okay, so that's the question. So in this question, we have to treat the ball as a point particle. That's the first thing we have to note. We have to treat it as a point particle. And the first question is saying show that taking g equals 9.8, v and alpha must satisfy this equation below. So this equation is 1 equals 4 tan alpha minus 78.4 over v squared sec squared alpha. So must prove that this expression is satisfied if we take g equals 9.8. We must show that v and alpha satisfy this equation. And part B is just saying use this equation, meaning this one, to find the required speed of projection when alpha equals 45 degrees. So here it is asked to find the speed of projection when alpha is 45 degrees. So now moving on to the solution. So the first thing you do to handle this problem is find expressions for the displacement, both the x component of displacement and the y component of displacement. So you see in this case we have the horizontal component is the x and the vertical component is the y. Previously in these notes we had the horizontal component which was the x as it is here, and the vertical component was the z in the notes, but this time our coordinate system we've chosen it to be the y instead of z. So instead of z here we have y, the vertical. So we have y as the vertical component of displacement. So now going back here to the solution, it is well explained. So we start with the x component of displacement where we say x equals v ix t plus half ax t squared. So this is just an equation of uniform motion. There's nothing fancy going on here. This is just an equation of uniform motion. And this is the x component of displacement. As you can see, so we start with x. So what's the x component of displacement? So from the question, we've been given that it is 4 meters horizontally. Now let's see what we have here. Okay, we have the 4 there. 4 equals, so the x takes the 4, equals vix. Okay, so this component of velocity in the x-axis is just v cos alpha times t. Okay, this is just v cos alpha times t plus 0. So this 0 is coming from the fact that ax here is 0. There is no acceleration in the x-axis. So the x component of acceleration is just 0. There is no acceleration experienced in the horizontal motion. So in the horizontal part of the motion, there is no acceleration. That's why it is 0. And it's right. It's written here: ax a subscript x equals 0. So from here, just this same expression, we can even make t the subject of the formula. So by us making t the subject of the formula, we'll have t equals 4 over v cos alpha. So just making it to the subject. So from now you get that expression and you name it as equation 1. Now moving to the y component of displacement, we have y is equal to v subscript iy, mean initial velocity in the y. So initial velocity, the initial component of velocity in the y-axis, times time plus half ay t squared. So ay here, acceleration in the vertical motion, is just gravity times time squared. So now the y component of motion, as you can see, the y component of displacement is just having a distance or a size of 1 meter there. This is just 1 meter. That's why it's been placed with the 1 there, is equal to viy. So the component of the initial component of velocity in the y-axis is just v sine alpha times the time, which is here, minus half a acceleration in the y-axis. This is just gravity, which is 9.8 t squared, and there's a negative here because gravity always points downwards, and we've assumed our coordinate system to be up positive, down negative, and right positive, left negative. So whatever vector is going up is positive and whatever vector is going down is negative. That's what we mean here. That's why our gravity is having a negative sign here. So say y equals v sine alpha 4 over v cos alpha. This is just the time which we made the subject of the formula. Here's this time here is what we replaced in there, minus half gt, the same t, this t takes the t in here, which is 4 over v cos alpha, then we square it, and then simplifying this expression further, you see there is sine alpha over cos alpha, which is just an identity which gives tan alpha, and this v will cancel with that v, and we just remain with a 4 and a tan alpha, minus this whole expression here, the product of 4 squared times 9.8 times half gives 78.4 over this v will be squared there, which is there v squared, and cos alpha is also squared in the denominator here, which is 1 over cos squared alpha here. Now cos squared alpha is also another identity, which is sec squared alpha, and you get this expression here. So you get this as the final expression, and yeah, by doing this we've solved and shown that v and alpha satisfy this expression. Now let's go back to the second part. Use this equation to find the required speed of projection when alpha equals 45 degrees. So let's look at alpha being equal to 45 degrees. So here we just take this equation and make v the subject of the formula. So the first thing that was done was to make this part containing v in it to cross to the left, and making everything on the right to cross back, and making everything on the left to cross to the right. So the only thing crossing is 1, and it's getting a negative there. And from here, making v the subject, you get this expression here, 78.4 sec squared alpha over 4 tan alpha minus 1. So this is the expression we're getting after making v squared the subject. Now to get rid of this square, we take square roots on both sides, and yeah, which is what is done here. And this sec squared alpha is taken back to its identity, which is 1 over cos squared alpha, and it appears in this form. And in the brackets here, we just have 1 over 4 tan alpha minus 1, which is this part in the denominator. So taking the square root of both sides, we get this kind of expression, where we now put back the value for alpha, which we've been given as 45 degrees. And by putting 45 degrees and punching this in the calculator, you get this expression. you get this as the final answer, which is 7.23 meters per second. So this is the velocity of this particle. Okay, so this turns out to be the velocity of our particle when the angle is 45 degrees. This is our velocity, which is the initial velocity. Now let's see the other question, which is just a short pattern, which is illustrated in the diagram. So this is the man who is throwing a shot in form of a projectile, as you can see the curved motion. So now this shot putter finds that he can project a shot a maximum distance of 20 meters. He wishes to determine the shot's projection speed. So that's what he wishes to do. He wishes to determine the shot's projection speed. So he wants to find out his speed of projection, which is the initial speed. And we've been given to take g equals 10 meters per second. Now, for this first attempt, he decides to consider the shot to be projected from the level ground. So for this first attempt, it's just decided that, okay, let's take the shots to be projected from the level ground. And using this model, we have to determine the minimum possible speed of projection. So assuming that the shot is projected from the level ground, not from some height as the man is standing. This man is assuming that is projecting this shot here from the level ground, somewhere here on the level ground, and then it goes all the way back to the horizontal. So that's the assumption. Now, using this model, determine the minimum possible speed of projection, which is V1, V subscript 1. And again, not satisfied with this value for projection, not satisfied with this value for projection speed, he decides to take account of the height from which the shot is projected. Okay, so now this time the man is trying to be more accurate. He's now taking note of this height, the height of projection. The first part is not considering the height. He is assuming that it's projected from the ground level, going up, then falling back to the ground. So, second part, this man wants to be more accurate. So I'll read the question again. Not satisfied with the value for projection speed, he decides to take account of the height from which the shot is projected. He measures this to be 1.5 meters. So in other words, what we're saying is that the distance from the ground somewhere where he's standing here to where he's holding this ball, it is now 1.5. Now, using this information, show that the range R of the shot along the level ground when projected from a height of 1.5 satisfies the equation 10r squared tan squared theta minus 2v squared r tan theta plus 10r squared minus 3v squared equals 0. So we must show that this range satisfies this equation when he measures the height to be 1.5. Okay, so and here it is saying where v is in meters per second, of course. V is the velocity in meters per second, the speed of projection of the shot, and theta is the angle of projection above the horizontal. All right, so let's look at the solution. So we'll start with A, where this is now the first attempt, right? Where he assumes this ball is projected from the level ground. That's the first assumption. So now we're going to calculate for displacement, both the horizontal and vertical components of displacement. So for the horizontal component of displacement, we use equations of motions x equals vi xt plus half axt squared And again, ax is 0. A subscript x is 0 because there is no motion in the horizontal direction. There's no motion, or rather there's no acceleration in the horizontal direction. That's why ax is 0. So this whole part becomes 0. The only thing we're going to work with is this part here. So now what is Vix? This is Vi subscript x times time. Yeah, I know it's not clear, but this is Vix, V subscript Ix times time. And when you look at x here, this is the displacement, which is the horizontal component of displacement. Okay, so this is the horizontal component of displacement, which is being given here as 20 meters. So you're saying that the short part finds that you can project a maximum distance of 20 meters. Okay, so this is how much you can project, maximum distance of 20 meters. So that's why we have 20 there. Being equal to Vi subscript x is just V1 cos theta, since this is the x component. V1 cos theta times the time there. This part we won't consider it because a subscript x is 0. So we have this as equation 1. When we put it like that. Now let's go to the y component of displacement, which is just y equals Vi y t plus half. Now acceleration this time, it's just gravity, which we've been told to take as 10, which is 10 meters per second squared, which is what I've written here as minus 10 t squared. The minus again is just showing that acceleration due to gravity is acting in the opposite direction as our positive axis. That's why it is negative here. So we have minus, since these two can divide with the 10, we have minus 5t squared there. And Viyt is just Vi sine theta times the time. Okay. And y here, this y component of displacement is 0. Why is that so? Because this particle is being assumed to be projected from the level ground, going all the way up and back to the level ground, meaning that the y component of displacement will be 0 because it has got back to where it started. So that's why the y component of displacement is 0. Okay, and 0 equals t. I've factored out t here since it's common. T open brackets v1 sine theta minus 5t. So we can have two equations. We'll have t equals 0 and v1 sine theta minus 5t. So the only part I've taken is v1 sine theta minus 5t, because if I take this part as t equals 0, t equals 0 is just the initial point of projection. Even if the displacement was 0, of course, because it was at the origin, the displacement was 0. Okay, so making to the subject of the formula from this equation in square brackets, we'll have t equals v1 sine theta over 5 and t equals v1 sine theta over 5. Take that as equation 2. Yeah, this part is now about us combining a and 2. Equation a and 2, which is a is this one, 2 is this one. We can combine them for t. This is just by substituting for t. So we can take this equation 2 here and put it in equation a. We're going to have this expression here. We're substituting for t on equation a here. And what we're having is this equation 20 equals v1 cos theta v1 sine theta over 5. Okay, and this 5 in the denominator can multiply with this 20 to get 100 here on the left, equals v1, and v1 can become v1 squared sine theta cos theta. We have sine theta cos theta there. Now we can multiply both sides of this equation by 2, so that we have this side 200, and this side we're going to have this expression. We have a 2 inside, as I am showing here. We have a 2 sine theta cos theta. Now 2 sine theta cos theta is just an identity, which is sine 2 theta, as it is written here. So here I'm just showing where it is coming from. It is coming from this expression in braces, this expression in braces there. And just from here, you can make v1 the subject of the formula by saying v1 equals the square root of 200 over square root of sine 2 theta. And it can be written in this form: v1 equals the square root of 200 over sine 2 theta. And there you have the expression for v. So you have the expression for v for the first attempt here. Now let's look at part B, where we have assumed the board to be projected from a height of 1.5 meters. Since now this one is more accurate, let's see what we're going to have. Okay, now we have something. Now I have something here. Here's a diagram which I made up. The diagram which I made up showing some details on the second part of the question. So this ball is being projected from some origin O, but this part is above the horizontal. Okay, it is above the horizontal, and the origin we've chosen as this point. Okay, so this origin, since it's above this 1.5 meters, and looking at our coordinate system, we've taken up positive, right positive. This means that this displacement from the origin going down will be negative, since we've chosen up as positive. So you should also always choose this when you're looking at the origin. The origin is somewhere in between, but our vertical displacement is below the origin, meaning that in our calculations we'll treat this 1.5 as a negative. It will have a negative since we've chosen up positive. Okay, the origin is here, this is the starting point, and our height is below the starting point. That's why it is even having a negative sign in the calculations. Okay, so here we have now y is equal to VIYT plus half AYT squared. Okay, so this is the expression which we're using to calculate for displacement. And here you have y, which is a negative here, negative 1.5, as you can see, minus 1.5 being equal to VIYT, which is V sine theta times time, minus again, because acceleration always points down and downwards is negative. That's why we're having a minus 10 there with the half and the t squared. So we take that as equation 1. Now for the range, you just go back here. The range is just the horizontal component of displacement, which is in the x-axis. So say r, the range, equals x v I xt plus half a xt squared. But r is just v cos theta. Since v cos theta is the horizontal component of velocity. So we say v cos theta times time plus 0. 0 is coming from this part here because a subscript x is 0. Now from here we can make t the subject of the formula, and we're going to have t is equal to r over v cos theta. So this expression is for the time, so we can keep it there, and then as having it here, we can now take this expression, okay, and substitute in the time in equation 1 here. So doing that, we're going to have an expression like this, which can also be simplified further by saying minus 1.5 is equal to r tan theta. Tan theta is just coming from sin theta over cos theta, which is just tan theta, and the v's will cancel here. Minus 5r squared, yes, over v squared cos squared theta. Alright, so we can multiply both sides of this equation by 2. So here we just multiplied both sides of this equation by 2 so that we get this expression. When you multiply this one by 2, you're going to get this right side by 2. You're going to get 2r tan theta minus 10r squared over v squared cos squared theta. And from there we can now multiply both sides of this equation by v squared. So we're going to have minus 3v squared equals, of course, this 2 was supposed to be in front of the r, but here I just put it as r2v squared tan theta, but you're supposed to put this 2 in front of the r. It's supposed to be 2rv squared tan theta minus, if this one also multiplies with the v squared, it will cancel with this v squared, and we're going to just have the 10r squared and 1 over cos squared theta. Alright, this expression can be written in this form as 2v squared r tan theta minus 10r squared, and this identity is just equal to sec squared theta. Now, this part, which is just sec squared theta, it is also an identity again, which is equal to tan squared theta plus 1. Okay, so sec squared theta becomes tan squared theta plus 1. And this part is just being repeated. It's been repeated. The only thing that is happening is that we're multiplying this minus 10r squared multiplied by tan squared theta. You get this. And minus 10r squared multiplied by this one, you get this. This expression, making every term on the right, or rather, yes, every term on the right jumping to the left side of the equation, we are getting this expression. And this expression is our final answer, and we've shown that we've satisfied what the question is asking us to do. So everything has been satisfied. That is the answer. Alright, thank you very much for joining me, and I'll see you in the next video.